Hi, and welcome to my XARC 12 conference presentation. My name is Magnus Haaland, and in this talk, I will present a fire experiment I conducted last year. But before we dive into the experiment, I will provide some background. I'm a geoarchaeologist working at Stone Age sites in caves and shelters. I studied the stratigraphy here by collecting sediment samples in the field and investigating them under a microscope. When you stand in front of some of these cave sequences that I'm currently working at, the white and grey heart features are quite striking. Here are two examples from which I collected block samples the previous years. One heart is in the top of this image, and the other one is at the base. In terms of behavioral information, these heart features can provide us with a lot of insight. The reason being that in the past, they served many vital functions, just as they do today. From a geoarchaeological point of view, my task is to decipher the hearts we observe in the field. We often do this through depositional formation models, such as the one you see here. Once you put a fire on top of a surface, it begins to alter it, and after a while the wood turns into ash and charcoal. If the fire is used many times, the ash and charcoal will accumulate, and the fire would contain combusted remains from multiple burning events. There is a range of factors that can impact the size, morphology, and microstratigraphy of hearts. I will not go into details here, but I can quickly mention fuel selection, the mode of fire, and post-depositional effects. Finally, we have a category that is only partially controlled by humans, such as air velocity, temperature, and humidity. If we go back to the complex heart we just looked at, my current analysis suggests that it was fueled by a large amount of dry wood, multiple times and over a longer period of time. Each fire was placed more or less on top of each other, and the substrate is characterized by being dry, flat, and sandy. To which degree this heart was subject to systematic heart maintenance, however, is not clear. Ethnographically, we know that these types of long-duration hearts often were subject to repeated and intentional removal of excess ash. During this process, the heart was partially removed, partially reshaped, and partially rebuilt, ultimately leaving behind a multi-generational combustion feature with a very complex life history. While many of the factors mentioned have already been studied in great detail, very few reports exist on the physical effects of systematic maintenance on long-duration hearts. The goal in my experiment is therefore to provide reference observations that may enable us to identify such practices in the archaeological record. The experimental design of my experiment was as follows. Two identical fires were made, number 1 and number 2. For wood, I used a species native to Australia, the coastal wattle. It also exists as an alien species in South Africa, where the experiment was conducted, and there it goes under the name Rooikrans. Each fire had two temperature probes recording the surface temperature and the temperature at 5 cm depth, every 30 seconds for the duration of the experiment. The fire was refueled by 3 kilos of wood every hour for around 10.5 days. All other parameters were kept as constant as possible, with the exception that the one fire was subject to ash removal 2 times. Because this was an open-air experiment, the environment was shifting, but we tried to shelter the fires as much as possible. You might have already seen the presentations of my colleagues explaining the recording strategy for our experimental season. I followed the very same protocol, including the collection of block samples. Just a quick note on the experimental micromorphology. The goal of this experiment, within the experiment if you like, was to collect undisturbed oriented block sample of each hearth. Ash, charcoal and beach sand easily collapses upon touch, which means that you lose its stratigraphic integrity very easily. A possible solution that I came up with was to impregnate the block samples in situ before removing the samples, by using epoxy resin and a slow working hardener. The experimental aspect of this was that I had never done it before and I had no idea if it would work. Now let's get to action. In this video clip, you will see the general setup of the experiment and the start of the fires on day number 1. Of course, Murphy's Law is never far away, so after around 30 minutes we got heavy downpour that almost managed to wipe the fires out completely. We countered Murphy by putting up sheltering plastic sheets on each side of the fire. In this video, you will see me removing the ash from one of the fires. I used a flat log to scoop it out. I stopped removing ash as soon as I reached the sandy substrate beneath. This is a complete overview of the fire experiment. We started the 22nd of February and ended it the 1st of March last year. We took surface photos of each fire every hour. This work required 5 people to work 6-hour shifts 24/7 for more than 10 days and was very labor intensive. On day 4 and day 8, one of the fires were subject to ash removal. In this video, you will see my experimental in situ block sampling procedure. I used metal tubes in the middle of the fire because even after 3 days, the fire was still hot in this area. In the periphery, I could use plastic tubes. The one half of the fire was then excavated. After the excavation was done, I finally poured epoxy resin into each of the sampling tubes. Some of the sampling results were great, as you can see from these pictures. The ideal result is characterized by a slow and gradual impregnation process. This avoids any volatile reaction to occur. The hardened samples typically have a uniform color and appears clear and transparent. However, not all the blocks I collected provided me with such an ideal result. In this case, the impregnation process happened very quickly, starting a chemical chain reaction that produced enough heat to make the resin boil. We think it might have been the heat stored within the sediments that may have triggered this reaction. However, the show had to move on. This is a video of the removal of the blocks once they had hardened. We sprayed water at the base of the samples before collecting them so as to prevent dry sand of pouring out of the bottom. This is a very general overview of the 2 fires from the start to the end. Fire 2, which I from now on have color-coded blue, was the one subject to ash removal on day 4 and 8. Fire 1, in red color, did not have any ash removed. Now let's look at some temperature results. This is a rather busy graph showing the surface temperature, the solid lines, and the temperature at 5 cm depth, the dotted lines, for each of the fires. It contains a lot of information, so I will guide you through a few basic points. First, we notice how the surface temperature of the maintained fire drops significantly each time the ash is removed. This is what we predicted. Second, it took around 3 days after the last refueling for the temperatures to drop below 40 degrees. Third, there were multiple periods with rain that reduced the temperature in both fires. Fourth, if we take a look at the air temperature and wind conditions, we note the predictable pattern where the temperature dropped below 20 degrees every night. The wind pattern is largely the opposite. Here we see that the most windy conditions, typically more than 2 meters per second, was primarily occurring during the day. While the maintained heart, blue solid line, appears to have been less affected by these environmental fluctuations, it appears that the surface temperature of the intact heart, the red one, correlates well with these fluctuations. To better understand the thermodynamics before and after the ash removal, I will now focus on 3 periods that were relatively stable and without major environmental fluctuations. As you can see, when we look only at these 3 periods in isolation, the environmental fluctuations are less extreme, and a general pattern emerges. The surface temperature of the maintained heart is kept stable about 500 degrees. The surface temperature of the intact heart is similar to the maintained one in period 1 and drops down to 300 degrees in period 2 and 3. At 5 cm depth, the maintained heart has a stable temperature around 330, whereas the intact heart temperatures drops around 50 degrees in period 2 and 3. The temperature difference of the dotted lines in period 1 we think is because the probe in fire 1 was put around 1 centimeter deeper than fire 2. We will now leave the temperatures and move over to the size of these hearts. We measured the ashy surface of the intact heart to be 0.55 square meters. The maintained heart was considerably smaller with a 0.41 square meter. In other words, the intact heart area was 34% larger than the maintained one. Now let us look at the profiles of these hearts. In terms of length, we measured the intact heart to be 92 cm and the maintained to be 66. In other words, fire 1 is 39% wider than fire 2. In terms of thickness, we note that while the intact heart is 13 cm deep, the maintained one is only 8 cm, making the intact heart 62.5% thicker. We can also assess the profile morphology of these hearts. From this figure, we can see that while the maximum depth below the baseline of each fire is quite similar, the intact heart is consistently deep throughout its length, while the maintained heart narrows quickly towards the periphery. We may also note that the height of the ash deposits above the baseline is quite tall in fire 1 and is relatively flat in fire 2. Fire 1 have a cone-shaped top, while fire 2 has a flat, irregularly shaped top. I will not go into too much detail on the block sampling results, other than saying that once we got them back to the lab and cut them open, most of them had intact sediments within them. However, many of them were only partially impregnated, which necessitated a second round of impregnation. In this slide, I have superimposed two block samples from fire 1. These two, the center and the periphery. And in a similar fashion, here you can see the blocks collected from heart number 2. I haven't had a chance to look at these samples in any detail. The take-home message here is that the microstratigraphy of the hearts seems to be intact. Even the boiling block sample, the red center, seems to have turned out reasonably well. So what did I find out in this experiment? Temperature-wise, the maintained heart kept a higher average temperature than the intact one. This was expected since the gradual accumulation of ash would have left the original surface probe in the intact heart buried under a gradually thicker insulating layer of ash. Size-wise, the intact heart was considerably larger and thicker than the maintained one. Again, not surprising, given that we actively removed a lot of ash. Morphologically, there is also a big difference. The intact heart exhibited a consistently deep base and a cone-shaped top, while the maintained heart showed a regular base and a flat top. While there is a difference in their microstructure, it remains to be studied in detail, and at this moment it is only to be continued. All in all, I think that what my experience show is that systematic maintenance of hearts significantly impact the physical configuration of long-duration hearts. What are the archaeological implications of my finds? Well, at the very simplest, I can only urge people watching this video that next time you encounter a complex heart feature in the field, remember how two identical fires burning the same amount of wood ended up looking completely different due to one single variable, heart maintenance. What did I learn during this experiment? Well, next time I'd like to use more temperature probes. I would place the probes more carefully. I would let the fire cool down before sampling it. The 24/7 burning experience wasn't ideal. I would also like to use wood from the local area rather than an alien species, and I would strive for a more sheltered environment that would become more comparable to a cave or a shelter. Before finishing this presentation, I'd like to acknowledge all the other experimental field season participants. The Center of Early Sapiens Behavior funded our field season. Isak Venter was our local fixer, moral support, and our biggest fan, and also a big thank you to Jungensfontein Karen Park and their friendly guests that allowed us to keep the fire going without complaining. and thank you for watching this video.